All right, so we'll start off by looking at the concept of balance. So balance is essentially the maintaining of homeostasis. So whatever we put into the body, we must eventually either use it or excrete it, and that needs to be maintained at a constant level. So if I'm drinking a certain amount of water a day, I must be producing a certain amount of urine per day, depending on how much my body is using water and how much water I'm producing. And so there needs to be a balance in between what I'm putting into the body and what I'm producing and what I am using and what I am excreting from the body. So the inputs and production should always be equal to the utilization and the output. And here we're really talking about water, but we can think about this in terms of overall caloric inputs and outputs, so energy, food. We can think about it in that term in that way as well. But here we're really looking at water when we talk about this type of balance. Okay. All right, so the kidneys regulate solute and water content. This also helps to determine our volume. We looked at a really good example of movement across the proximal convoluted tubule, and we saw this really important principle where the movement of water follows the movement of solute. And so the kidneys help to regulate solute, and in doing so, they also regulate water. So this is why patients with high blood pressure typically also store water, and they become swollen, they get edema, because the solutes are not leaving, and so the water is not leaving, right? High solute concentration is followed by high water concentration. And so this is where the kidneys come in balancing our water and blood volume, but also they help to balance our acid base as well. And we'll talk more about that in the final packet. So the composition is also affected by the exchange that's taking place between all of our different body compartments. So when we're speaking about water inputs and water outputs, we're talking about what's happening on a cellular level. We're talking about water that's stored in our bones, in our blood, in our plasma, water that's in our other forms of connective tissue, so tendons and ligaments. There's a small amount of water that's stored there in those connective tissues. There's water in the GI tract, right? Lots of water, whatever we bring in from the diet, whatever is secreted into the GI tract is also exchanged there. And then we've got things like sweating and respiration and some other smaller inconsequential processes as well. So there's always this exchange taking place between these compartments as well as between the plasma, which is where most of our water is circulating, okay? All right, so our second objective here is to describe the different sources of body water input and body water output. Okay, so let's take a few questions. Okay, so can we go over the checkpoint questions from the last slide and the last packet? Okay, and then, yeah, someone is seconding that. So I will go over those. Let me close this. I think I did ask you guys to craft some responses to that. So let me go back to, okay. All right, so just to go over these checkpoint questions, the first one, name 3 structural differences between the epithelial cells of the proximal and distal tubule, and then the structure of which tubule is more favorable for exchange. So we talked about the difference between the epithelial cells of the PCT and the DCT. One, they had more of a tight junction, right? The epithelial cells of the proximal tubule, here they go, they have a leaky tight junction, rather, so they can facilitate movement that's going from the lumen into the capillaries. 2, they have this brush border, which is also made up of this microvilli. Okay, and then 3, these are actually taller cells. These are columnar cells. So these are different cells altogether. And I don't think we really talked about the types of cells, but these are different cells altogether. They're taller. They've got this apical modification, which we call microvilli, that forms this brush border. And then they also have this leaky tight junction, which facilitates the movement in between these 2 cells. The distal collecting tubules are different in that they don't have microvilli. These are shorter, more cube-shaped cells. These are cuboidal cells. They have a tight junction, so there's absolutely no movement, no paracellular transport in between these cells. And so this is very heavily regulated, whereas the PCT is very unregulated, okay? So there's free movement, whereas here, there is not free movement in between cells. Yeah, and those are some of the main differences between the PCT epithelial cells and the DCT epithelial cells, okay? Let's go back here. The second question, it said, which structure was more favorable for exchange? And that's going to be the PCT, right? Because we can have not only movement that's happening through the cell itself, but we can also have that leakage that's happening in between, or that paracellular movement. And then we also have the brush border, that those microvilli, the modifications at the top of the cell, are a modification that increases the surface area, which helps to make exchange more favorable. Question 2, the clearance of which two substances can be used to estimate GFR, and the clearance of which substances can be used to estimate renal plasma flow. Okay, so we didn't get into the details here, but the two substances that we said were synonymous to GFR, if we go back to this table, were inulin, because inulin is the exact same clearance rate as GFR, as well as creatinine to some extent, right? It's not very far from the GFR. So we can use these two substances to speak about GFR and to tell us how well our GFR is, right? How efficient the kidneys is in terms of the GFR function. And then the third part of that question is which substance can be used to estimate renal plasma flow? Now, again, we did not speak about this in detail, but PAH, right? This para-aminohepatic acid is what we use to estimate renal flow because it has the highest clearance rate. So it's going to tell us the most about the flow of blood that's coming through the kidneys. Okay. And don't be too bothered, excuse me, with those other substances like inulin and PAH. We didn't talk much about them, but just to kind of answer this question, I'll point those out. Number 3, if the clearance of molecule X is greater than GFR, was it reabsorbed or secreted in the renal tubules? So we said if the clearance is greater than the GFR, then it must be secreted. And if the clearance is less than the GFR, then it must be reabsorbed. And if you kind of break that down, it'll make a little bit more sense. If I'm spilling more of this thing than what I filtered into the urine, then I must be getting more of it from somewhere. It must be secreted from the blood into the tubule. And the opposite is true. If I'm spilling less of what I filtered into the urine, then some of it went somewhere, right? It must have been reabsorbed and it must have gone back into the capillaries from the tubule. And so if we look at things like, again, creatinine. Creatinine is secreted because it has a higher clearance rate than the GFR, whereas if you look at glucose, glucose has a clearance rate of 0. That means it is fully reabsorbed and we shouldn't see any of it in the urine. All right, and then number 4, describe the innervation of the bladder, internal urethral sphincter, external urethral sphincter, and then voluntary inhibition of micturition through innervation to which of these structures? Okay, so the innervation of the bladder takes place with 2 different parts of the nervous system. We've got the internal sphincter, smooth muscle. This is involuntary, so this is going to be the sympathetic and parasympathetic innervation. And then the external urethral sphincter is skeletal muscle, which we are controlling, so this is voluntary control, and that is going to be the somatic division of the nervous system. Okay, and then voluntary inhibition of micturition, so basically the ability to hold urine, even if you have to urinate, happens through innervation to which of these structures? So that's going to be the external urethral sphincter, right? The only voluntary portion of this is what happens with the external sphincter, okay? And we talked here about how the integrating centers, the central nervous system, specifically the pons, is controlling the sympathetic and parasympathetic innervation to the internal sphincter, as well as to the bladder muscle itself, the detrusor. And those things we do not control, right? When we have stretching on the bladder because of the amount of urine that's filled, those signals are sent to the brain and that autonomic communication happens involuntarily. But the voluntary inhibition, so the preventing of urination voluntarily, is the innervation to only the external urethral sphincter, which happens via the somatic innervation.